So we're going to take a look at the basics of thermochemistry, specifically pertaining to energy. So the nature of energy is directly related to thermochemistry. So understanding energy is going to allow us to understand the concept of thermochem. So energy is the capacity to do work or produce heat. So whenever we're looking at our analysis of energy of a system or chemical reaction, what have you, we're going to be looking at work that's produced or heat that's produced. These are the two ways in which we're able to understand and calculate and measure and basically ascertain the energy of a specific system. And we'll talk about that in more detail. Now, the law of conservation of energy tells us that energy is always going to be conserved. So what do we mean? We mean that energy can be converted from one form into another, but is never going to be destroyed. And this is directly connected to the first law of thermodynamics, which we'll discuss a little bit later as well. So energy is going to be looked at from the perspective of either being potential energy or kinetic energy. Potential energy is going to be energy due to position or composition. So something sitting up on a high shelf would have potential energy of position. The gas in your fuel tank in your car would have potential energy due to its composition. And we'll talk about some more of this in a minute here. Now, kinetic energy is the energy due to motion. Now, it's expressed by this equation here. So kinetic energy is equal to half the mass times the velocity squared. So you can calculate the kinetic energy of an object, if you know its mass and its velocity. The interplay between kinetic and potential energy can be best diagrammed by what we see here. We have an initial state of a red ball and a blue ball, and we have a final resting state of those same two balls after the exchange of energy has occurred. So notice the red balls and the blue balls are in different positions, but it's still the same diagram. It's just an initial and final state. So what do we see here? Initially, we have the red ball here in an elevated state. We have it in a higher position. So its potential energy is higher than the potential energy of the blue ball that we see here. When the red ball is released, its potential energy is converted into kinetic energy and it moves down the hill. As it moves down the hill, it strikes this blue ball and transfers its kinetic energy into the blue ball. The blue ball subsequently moves up into this elevated state, and you have a final resting state of both the red and blue balls. So we can see the exchange or the interplay between kinetic and potential energy. We see that the potential energy from this red ball was transferred into kinetic energy. That kinetic energy then was transferred into the blue ball. The blue ball then attained a new position, which now rests as a object that has higher potential energy than it originally did. Now, what allows this to happen? Well, we have to look at the interplay between the energies. Okay, well, the kinetic and potential energies are very clearly seen. However, if you notice, the final resting states of both the blue and red ball are drastically different from the original red and blue ball. The potential energy of the blue ball has increased, and the potential energy of the red ball has significantly decreased. However, the original position or the original potential energy of the red ball has not equally transferred to give you the same potential energy of the blue ball. Notice the blue ball is in a lower state in terms of potential energy than this red ball originally was. So because of that, there has to be something else that is affecting or being released or gained in order to basically cause this overall decrease in potential energy. What are those two components? Those two components are going to be work and heat. So work and heat are both being transferred in this type of interaction. So let's look at work really quickly. So work is a force acting over a distance. When the red ball strikes the blue ball and transfers its kinetic energy, this blue ball moves to a different position. Okay, the force of the red ball gets transferred into the blue ball and moves it. This is work. So some of the energy is lost during that exchange. The other energy loss is going to occur in the situation of heat. Now, whenever a ball or roller skates or tires or any other substance rolls over a surface or slides over a surface, you have friction, and friction creates heat. The release of energy, or the release of this potential energy as we go from potential energy into kinetic energy as it starts to move, is not going to be a direct transfer of potential energy to kinetic energy. As the ball rolls down the hill, energy is lost because the frictional heat that gets created is going to basically dissipate the energy of this ball. Same thing occurs as the ball rolls along the little hump here and reaches its final resting place. So both work, okay, so basically the transfer between the red and blue ball, that's going to cause the energy change, okay, and the difference in the final and initial states of the balls, and heat. Okay, so these are going to be the two components that dissipate the overall energy of this system. And the reason why we see such a difference between the final resting states of the blue and red balls compared to their initial states. So what we've seen here from this diagram is basically a nice illustration of the law of conservation of energy. Remember that energy is neither created or destroyed, it's only converted from one form to another. So we've very easily here seen how potential and kinetic energy have a nice interplay when we're going from this initial to the final state. Work and heat come into play to basically allow us to understand why the final position is so drastically different from the initial. If work and heat were not present, we would expect an equivalent change in terms of the height of this blue ball versus the red ball. However, because of the loss of energy in the form of work and the loss of energy in the form of heat, the initial and final positions are drastically different. Now, what one needs to make sure they're understanding is that the total energy of this system is constant. Okay, if we were to sum up the energy associated with the heat, the work, we would overall see that the total energy of the system here versus here are exactly the same. However, we end up with a very different result because the work and the heat transfer options create a disparity between the potential energy of that red ball and the potential energy of the blue ball at their final states. A state function is basically a property that allows us to determine the state of a system regardless of how that state was achieved. So basically, we ignore mechanisms, we ignore routes that were taken, we ignore procedures for state functions, and only look at their current state. And we can compare two different state functions if we know their initial and final states. It doesn't matter the route that they took. Now, we look at these two hikers and we can compare them. If their position is a state function, notice that the routes that they took to get to their position from their initial state are drastically different. However, because this position or the system is a state function, we can ignore the meandering route versus the more direct route that was taken by each of the individual hikers. So in the previous example that we looked at, the energy of the red ball and the blue ball, the overall energy of that system is a state function. It doesn't matter how their exchange of energy occurred. It didn't matter if energy was lost by frictional heating or if it was lost through work, whatever the process was. All that matters is the final state of that situation or that system. Now, what you must understand is that energy in that situation is a state function. We can ignore the route. Heat and work, however, are not state functions. So you would, if you were asked questions about heat or the work of that system, you would need to account for their actual procedures. So we've been using some vocabulary that needs to be more clearly defined. So yeah, basically, chemical energy is the potential energy associated with chemicals. So methane or propane or the gas that's in your fuel tank in your vehicle, these are all examples of chemical energy. There's potential energy in the bonds of those molecules. So when we look at CH4 or methane, we know that it has potential energy. It has the ability to create heat or energy in the form of heat. Now, in order to analyze chemical energy and chemical reactions, so things like this, we must be able to identify what we're looking at. And describing what we're focusing on gives us the opportunity to be able to clearly discuss what's actually happening with respect to the chemical energy of that reaction. So let's first look at our definition. So a system is a part of the universe in which we're focusing on. So the system might be the container in which the reaction is occurring. And usually for chemical reactions, it is the container in which the reaction is being held. The surroundings include everything else in the universe, so everything that's surrounding whatever we're focusing on. There's also different system types. There's open systems, and with an open system, heat can be exchanged as well as mass or matter, so things can leave the container. A closed system doesn't allow for the mass exchange to occur. Because it's closed, only heat can be exchanged. And an isolated system is one in which, theoretically, neither heat in the form of energy or mass of the substances inside the container would be able to leave. So the system, remember, is a thing that we're focusing our attention on, and our surroundings is everything else that's not part of the system. And this is going to be important for us to understand heat flow, energy exchange, and things of that sort. So if we're looking at a chemical reaction and we're focusing on the system, the heat exchange that may occur is going to be described in one of two ways. It's either going to be exothermic or endothermic. An exothermic is a reaction that gives off heat or that evolves heat. Now, an exothermic reaction is going to be losing energy in the form of heat. Now, if we're taking our previous slide and we're thinking about the system, okay, a reaction container that has an exothermic reaction, it is going to get warm. It is going to release heat. An endothermic reaction is a reaction that absorbs energy in the form of heat from the surroundings. Okay, so in those situations, in terms of an endothermic reaction, a lot of times heat is going to be being pulled from the surroundings into the system. So why is this important? Why do we need to think about this? Well, all of the interplay that we've just discussed between potential energy, kinetic energy, work, heat, all those are directly related to chemical energy. So instead of looking at the interplay between the position of the red ball and the blue ball, in this situation we're going to look at the differences in energy between reactants and their subsequent products. And basically what we have here are just little mini energy diagrams. Please notice the energy arrow on the left-hand side of both of these reaction types. The representation here shows how we go from having a certain quantity of potential energy, either higher or lower, in those chemical reactants, and how that subsequently plays into the production of heat or the absorption of heat in the specific reaction being viewed. So let's go ahead and look at the exothermic reaction here. Notice my reactants are starting out at a higher energy state than my products. Okay, so when I go from reactants to products, basically energy is going to be being released. In this situation, energy is being released in the form of heat. So the transfer or the energy change that we see from between reactants and products is conserved because some of that energy is given off to the surroundings as heat. This conservation can be better diagrammed if we look at the endothermic or an endothermic reaction. So the reactants in this case are of lower energy than the products. Okay, so in order for us to go from a lower energy reactant to a higher energy product, energy must be put into the system. So in this case, we're looking at an endothermic reaction because that energy must come from somewhere. So energy is absorbed from the surroundings in order to give us our new higher energy products. So the interplay, or that law of conservation of energy, is directly related to our reactant and our product states, as well as whether heat is absorbed or expressed from the reaction type. So exothermic reactions are going to evolve heat, so they're going to give off heat because we're going from reactants that are in higher energy state to a lower energy state. And endothermic reactions are going to absorb heat from the surroundings because we're starting with lower energy products and wanting to get into higher energy product states. So this interplay is diagrammed nicely here with respect to chemical energy. It's the same concept as seen with the red and blue ball that we saw earlier. However, this is more useful with respect to chemistry and subsequent chemical reactions that we may be looking at. The internal energy of a system is the sum of all the kinetic and potential energies of all the particles that are in a specific system. So whatever you're focusing in on, that system's internal energy is going to be related to all the particles' kinetic and potential energy features. This delta E that you see here is the change in internal energy of a system. And that can be represented by the equation here, which shows that the change in internal energy of a system is equal to Q plus W. Q is the heat exchange between the system and the surroundings. Remember, the system is what you're focusing on, and the surroundings is basically everything else. W represents the work that is either done to or by the system that you are applying your focus. So, now, the thermodynamic quantities that we're going to be looking at are always going to have two components. They're going to have a number and they're going to have a sign. The number indicates the magnitude of your change, and the sign indicates the direction of change. And we are going to be looking at these values with respect to the system. Other sciences look at it from a different perspective, but in terms of chemistry, and most chemistry texts are going to look at it with the perspective of the system being the thing you're focusing on. So remember that our change in E is dictated by the sum of the value of Q and the value of W. And Q represents heat and W represents work. So when work is done by the system, so when the system that you're focusing on does work onto the surroundings, your W value will be less than 0. So then it'll be negative. If work is done to the system, so if a piston is pressed down or something of that sort is done to the system, your W value for that specific system will be positive. In that same vein or that same thought process, if a system loses heat, your Q value or your heat value is going to be negative. If the system gains heat, the Q value will be positive. So these types of numerical values will be plugged into the equation here, and that will dictate the overall change of delta E. So depending on what happens with the heat and the work, you may have a system that's losing energy or a system that's gaining energy. It just depends on what's actually happening. So let's go ahead and let's look at some practice problems. This question tells us to calculate the delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done onto the system. So remember from our previous slides, our delta E is equal to Q plus W. Now, they've given us the values, the numerical values for Q and W, respectively. However, they have not given us the signs. However, based on the way the question is written, or based on how it's been presented, we can determine the sign of each of these. So, calculate delta E for a system undergoing an endothermic process. Remember, endothermic reactions, the system is gaining heat. Okay, so in this case, your Q value or your heat value is going to be positive. So the 15.6 kilojoules is a positive value. W, on the other hand, let's go ahead and take a look at that. Okay, where 1.4 kilojoules of work is done on the system. So the system, work is being done to the system. Because work is being done, it's going to be a positive value. So 1.4 kilojoules is what we're going to have here. Now, before we go ahead and plug our Q and W value into this equation, we want to make sure that something matches. We always have to check this anytime we're summing up units. Making sure that our units match is very important. In this case, kilojoules and kilojoules is what both of the units are in, so we can subsequently sum them. If one was in joules and the other in kilojoules, we would need to make an adjustment to one or the other before we could make this summation. So delta E is going to be equal to 15.6 kilojoules plus 1.4 kilojoules. Okay, and that's going to give us 17.0 kilojoules for our delta E value. Notice we've done a summation here. The least number of digits to the right of the decimal is 1, so our answer should have 1 to the right of the decimal as well, giving us overall 3 sig figs in our final answer. So, basically, you want to make sure that your units match here. You want to find your signs of the values that they gave you based on what the question tells you. If it tells you it's endothermic, you know heat's going to be coming into the system. If it's exothermic, heat would be leaving. If the system is experiencing work or work is being done to it, W would be positive. If it was doing work, W would be negative. So taking this approach and taking these steps will allow you to calculate these types of calculations in a very straightforward manner. The problem that we're looking at here is a pressure volume work type calculation. And basically what we're trying to look at in this type of a question is to figure out how much work is done to or by a system based on the expansion or the compression of a gas. So if we're looking at a system in which we have a gas that's inside a piston, it's going to change in some way. It's either going to expand and work against an external pressure, or it's going to decrease in terms of its overall volume. Okay, it's going to compress based on its interaction with an external pressure. So this pressure volume work type calculation is going to utilize this equation. So work is going to be equal to negative P times delta V. Delta V is representing this change in volume that's occurring within a piston or some apparatus similar. And P is representing that pressure, that external pressure that's being applied to the system. Now, if delta V is a positive value, what that means is that the piston is expanding, okay? The space is increasing. So delta V in that situation would be getting larger. It would be a more positive value, okay? However, it would also be doing work on the surroundings. If delta V is representing what's happening to the system, it's expanding, that would mean that the piston, okay, is also expanding up and acting against an external force. Now we know that when W is positive, work is being done to the system. And when W is negative, work is done by the system. The equation that we see here accounts for this need to have the appropriate signage, and we'll see this in the example calculation that we're about to do. So if we look at what they've given us, so they've told us that we have a gas that's expanding from 46 liters to 64. So our delta V is going to be 64 liters minus 46 liters. We are going from a smaller volume to a larger volume. So our V final minus our V initial is going to give us a positive value. Now, if we look at this equation over here, our delta V value would be positive. If the negative sign was not included in this equation, that would give us a positive W value. Now, a positive W value represents work being done to the system. However, we know that this piston is being pressed up, or this volume here is expanding, and because this is the system, we know that the system is actually doing work to the surroundings. So we know that our W cannot be positive. This is why the equation is written as it is. This negative sign helps facilitate the appropriate signage associated with W. So let's go ahead and finish the calculation up. So 64 minus 46 is going to give us 18 liters. Okay, so these 18 liters is what our change in volume is. Notice the sign is positive. We are then going to plug this 18 liters into our work equation. So W equals negative P, in this case P is 15 ATM, times our delta V, which is 18 liters. Okay, so our work is going to be negative 270 liters times ATM. Now, we could convert this answer here into joules by using this following equation, or this following proportionality. So 1 liter ATM is equal to 101.3 joules. Okay, so this is a conversion factor to kind of know. It'll come up later. But in this case, they haven't indicated what units we need to give our final answer in. So liter ATM is completely acceptable. So with these types of calculations, remember we're utilizing this equation here. Understand that the negative sign in that equation is allowing us to account for the signage, the appropriate signage associated with work being done to or by a system. We just want to make sure that we're identifying what the system is, the appropriate sign for our change in volume. Obviously, if we're expanding, our delta V should be positive. If we're being compressed, our delta V should be negative, and that will subsequently indicate the type of work that's being done either to or by the system. So now we have a problem that's going to be utilizing all of the skills we just learned in the previous problems. We're looking at a balloon that's being inflated by the heating of the air inside the balloon. So basically they're going to give us information about initial and final volumes. So our final volume of the balloon is 4.5 times 10 to the 6th liters. Our initial volume was 4.0 times 10 to the 6th liters. Okay, so we have information about our volume changes of the balloon. We know that heat has been absorbed by the balloon. Because of that, we know that we have our Q value of 1.3 times 10 to the 8th joules. Okay, so we have volume values, we have a heat value. We've also been given a
pressure value of 1.0 atms. Okay, and they want us to calculate delta E. Okay, so they want to know the change in the energy for the process occurring at 1 atm when a balloon goes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters upon the addition of 1.3 times 10 to the 8 joules of energy in the form of heat. Okay, so basically what we're saying is we're taking a balloon and we're increasing its volume by the addition of heat. So the way we're going to calculate this is by utilizing the delta E equals Q plus W equation. Now, I know Q, that was given to us. It's positive because the system is going to be accepting or absorbing heat. W, on the other hand, must be calculated using the equation that we see here. We need to figure out the work associated with the volume change occurring against the constant pressure value. So W is going to be equal to the negative 1.0 atm times our change in pressure, which is going to be delta V, which is equal to Vf minus Vi. So in this case, 4.50 times 10 to the 6 minus 4.0 times 10 to the 6. That is going to give us a value of 0.5 times 10 to the 6th, or 5.0 times 10 to the 5th for our delta V value. And we're going to plug this in here. Okay, so our work value that we're going to get is going to be negative 5.0 times 10 to the 5th liters times atm. So we now have our work value. We already had our Q value. And normally we would just plug those into this equation here in order to get our delta E. However, the problem that we have is that the units don't match. The units for Q, for our heat value, are in joules, while our work values are in liters times atm. So as I said earlier, there is a conversion factor that allows us to convert between joules and liters times atm. So work is going to be equal to the following times 101.3 joules for every 1 liter times atm. Okay, go ahead and plug those in. Units cancel out there, and our work units are going to be equal to negative 5.1 times 10 to the 7th joules. So now that we have both Q and W in the appropriate units, we plug them into this equation to get our final answer. So what we're going to do there is delta E is going to be equal to 1.3 times 10 to the 8th joules plus negative 5.1 times 10 to the 7th joules. Okay, and this is going to give us an overall delta E value of 8 times 10 to the 7th joules. And this is the energy change associated with this balloon being inflated by the heating of the air inside. So we get a positive overall delta E value right here, which makes sense because the system has absorbed a fair quantity of energy as heat and as it subsequently expanded. So the system that we're looking at has experienced a positive change in internal energy. So when we're doing problems like this, we want to write out all of our variables. We want to make sure we know our appropriate equations, such as this one and this one here. These are going to be important for calculations on quizzes and exams. We want to pay attention to our unit conversions. So we talked about this one right here. talked about it previously in another slide, and it could be useful in any future quizzes or tests.